All right, let's take a look at this here. Equation 616, what is that? Equation 616 is Dalton's law. The total pressure is equal to the sum of the partial pressures. So the partial pressures add up to the total pressure. With Dalton's law, the volumes are constant. That's equation 616. Unfortunately, they didn't give a number for this equation. This equation is called Avogadro's law. Avogadro says the total volume is equal to the sum of the partial volumes. Okay, this should be 617. And then here's both of them together. Both of them together, the mole fraction is always true. The partial pressures are true when the volume is constant. In other words, the pressure fraction. The volume fraction is true when the pressure is constant. And so this is Dalton's, this is Avogadro's, and this is the mole fraction symbol. All right, these keep in minds are important because, in order to use 16, what has to happen with the volumes? They're all equal. When we use this equation, which should be 617, but this is 617, so we'll call this 616b, the pressures have to be equal. I'm glad they put this in. They didn't have this before. Okay, but we're okay. And so let's look at an application of this. One of the most common applications of gas mixtures is obviously chemical reactions. If you have a chemical reaction, you got to mix the reactants together. We'll look at that later. Another common application of this, actually, let's just look at this. We'll do a chemical reactions application first. So an example would be, let's take some hydrogen gas and mix it with oxygen gas. This is going to produce, let's say, H2O liquid. It's a redox reaction. All right. In terms of mole fraction, this is pretty straightforward. In other words, balanced chemical equation is in terms of mole ratios or mole fractions. And so here, 2 out of 3 moles of reactants will be hydrogens. Mole fraction is 2 out of 3. Mole fraction for oxygen is 1 out of 3 moles here. And so we need to mix 2 moles of hydrogen, 1 mole of oxygen, right, to do this, let's say, or anything in that ratio. And so this is always true. Or alternatively, if the mole fraction is like this, then the pressure fraction will be the same. And so what we could do is we could do 2 atmospheres of hydrogen and 1 atmosphere of oxygen. That's going to be the same ratio, right? And so if we wanted to do this reaction, because measuring out moles sometimes isn't easy. Normally, if you want to figure out how many moles you have, you measure the volume or the pressure, or both, right? Volume and pressure. Actually, you need to measure both. And so if I do this, then I have a stoichiometric ratio of hydrogen and oxygen, and I can let it react. But what's the volume? This would be the pressure of the hydrogen. What would the volume of the hydrogen be? And what would the volume of oxygen be? Okay, if I mix 2 atmospheres of hydrogen, would the volume of hydrogen be twice as big as the volume of oxygen? Yes or no? Or what's my total pressure going to be? If I take 2 atmospheres of hydrogen and pump in 1 atmosphere of oxygen, then P total will be how many atmospheres? How many atmospheres total do I have? Well, altogether, I'm going to have 3 atmospheres of gas in my container. And the container, well, the container is going to be, what is the volume of the container? The volume of the container will, the volume of the container is V total. And V total will equal V hydrogen plus V oxygen? It could, but you know, V hydrogen and V oxygen will, everything's in the same container, so it's just one container. And it has all the gases.